Okay, so we were discussing about the ductility. The That's the most important aspect of resisting earthquake effects in buildings and also in other structures, but more so, very critically in case of buildings. Uh, that makes a difference between the economically viable projects and very very expensive, out of bounds kind of costing that we look at for earthquake resistance. So ductility, as we discussed yesterday in our last lecture, uh, we have multiple definitions of ductility, and the most important one that refers to mechanics wise, the most important one is the curvature ductility that captures the mechanics of seismic action in any structural member. So typically your ductility is defined as mu maximum displacement, maximum strain divided by yield strain. That's the material testing kind of definition. This is the classical way ductility is defined based on uniaxial test specimen. But we look at curvature ductility. Curvature ductility is referred to by ratio of two curvatures, maximum curvature divided by the yield curvature. Now, how do we estimate what is the yield curvature and what is the curvature itself? You may refer to the classical engineering theory of beams, bending of beams. If you recall, M by I is equal to E by R, or alternatively E times phi. So 1 over R is the curvature, and that is equal to sigma by y, the axial stress, divided by the distance from the neutral axis. So that's the Euler-Bernoulli engineer's theory of beam. Right. So phi, as you know, 1 over R, or also referred to as the curvature. This is essentially so rate of change of the slope per unit length. Not exactly slope. In this case, slope and rotation are synonymous, so that's why it works out that way. So section rotation per unit length. So how do we determine, in order to find out what is the maximum curvature and what is the yield curvature, how this yield curvature is very critical, to estimate. How do we estimate the yield curvature? Without that we cannot compute the displacement ductility. the yield level has to be defined first. Otherwise, how do we compute the ductility? The denominator has to be known. This, of course, we can estimate from the maximum deformation, whatever is happening, and it can work. It can be worked out. Because contrary to what we do in case of uniaxial tension specimen, there is no definite yield point for curvatures, right? So this is characterized by material testing, is characterized by definite yield points, or it is well defined. How do we know what we consider as yielding, and also the maximum strain. But no such definition the moment curvature relation is not very clearly, I mean, there are no definite yield points. So typically M5 relationships, they may look like so the curve may actually look like something like this. So actual moment curvature relationship looks like this. So it's a non-linear function, and there is no definite yield point, if you see, because if you try to visualize the hinging pattern, how does the plasticity, how does the section incur the plastic deformation? The plasticity gradually penetrates into the depth. So initially the strain distribution across the cross section is linear, and epsilon c and epsilon s, and then slowly you will find that it becomes yield, it begins to yield, and then for some element, some constant, it is there. So this kind of scenario, so the depth, slowly it gradually it develops, cracking etc. happens, and then once the concrete also begins to crumble, concrete in compression, then it will also try to accumulate and the constant strain, and slowly the entire section will become plastic, will develop into a plastic hinge. So it's a gradual process, and that is what is reflected here. So gradually, as the curvature increases, uh, cracks develop, the section plastic deformations accumulate slowly, and until the point when it reaches the ultimate maximum curvature, when the entire section is and there is no further capacity to sustain support the load, then the entire section, uh, uh, that's the collapse point. So eventually it is idealized as a bilinear. For the purpose of idealization, we consider it as a bilinear system, because this non-linear so this bilinear variation, and this is what we call as yield curvature. Now this yield curvature is often defined at the from the point of when the steel reaches the yield strain, then what is the yield strain, and divided by the distance to the neutral axis, right? So d, so if this is neutral axis depth and this is effective depth, then curvature is given by yield strain divided by the length length of this base. So this is what we call as curvature, phi y. If this is yield strain, steel in the strain in the steel, tension steel is equal to yield strain. However, if the reinforcement area is too large, it's a heavily reinforced section, then it may be possible that the concrete may achieve its concrete strain may be approaching the cracking values, right? It may achieve its maximum strain before the not maximum strain, the peak stress curve in compression, unconfined compression in concrete. So then this phi y can also be computed as epsilon c divided by the neutral axis depth. So then epsilon c is often taken as 0.0015 of the order of. So it is not the ultimate strain. If you look at it, ultimate strain of unconfined concrete is about double of that, and this is the strain at which you have the maximum stress developing in the concrete. So we compute what is the maximum, the maximum stress will develop at a slightly higher value than this, about 0.002 strain level, and this is slightly lower, and that is for the modeling of elastoplastic concrete stress strain. So using this strain level, we can compute whatever is the curvature at the yield if the section is very heavily reinforced. So the point is we need to estimate this yield curvature to find out what is the curvature ductility, and eventually you will find that curvature ductility is often fairly large. It is almost consistent about the consistent with the values that you typically observe for material testing ductility. So mu phi typically right. Now that is only for a particular section. I mean, plastic hinge develops. If you recall the mechanism of deformation in a structural system, these plastic hinges actually develop only at very small finite region. Right? So so these are the plastic hinges, and we designed them to be developing in the extreme ends of the beam, and this curvature ductility that is available, that is valid only over this plastic hinge region. Now what is the length of this plastic hinge? How far? I mean, this is what we are looking at, a cross section, but then it takes some length to plasticize. It cannot be just at a one particular section only, one particular value at a specific point. Obviously, it has to be spread over certain length, right? So there has to be finite size for plastic hinges, right? So what is this finite size? So this is commonly referred to as plastic hinge length. So what is the length of the plastic hinge? So that is where the curvature is considered to be completely constant plastic curvature, and that's the entire section. Curvature is considered to be constant. It is no longer, I mean, if you look at it, the curvature also keeps on changing from the distance, with distance. So as you consider the deformation, let's say cantilever beam. If you consider a cantilever beam, I will draw it as a vertical cantilever, it's easier. So carrying a constant moment. So the bending moment diagram, of course, is a constant bending moment. So there is P, and this is total length L. So this is, of course, PL is the bending moment, maximum bending moment, and the curvature obviously is going to be elastic curvature phi is equal to m by EI. That's the curvature according to beam theory, elastic beam theory. Now after the plasticity sets in, then this begins to plastify. I mean, it increases. This is elastic, and as the moment increases, as the capacities are exceeded, the curvature, it remains elastic, and then this was the initial elastic distribution, and it begins to deviate. So this is what original phi p and phi e. And over a period of time you will find that this is constant. This curvature, plastic curvature, is constant over certain length of the beam, and this is called, over which plastic hinge length, right? So this is different from, plastic hinge length is different from inelastic region. Region of plastic deformation. Okay, let me. So region of plastic deformation. So these two things are two different things. The length over which the plastic deformations are happening is different from the plastic hinge length that we consider. So this plastic hinge length is the length over which we can consider the constant curvature that prevails, maximum plastic curvature that prevails, and that is used for this is considered to be concentrated at the midpoint of this length hinge, and this is useful. The basic idea behind this construct is to be able to use simple kinematical relations to predict the displacements. So curvature can be used to predict the displacements, and that is how it is worked out. I mean, this simple relationship. So that's the idea of plastic hinge length, that it allows you to calculate what is the displacement is going to be using simple kinematical relations. For example, the tip displacement can be referred to as is proportional to, I would say, phi L square, right? So that's the tip displacement, that is proportional to phi L square. As you can very well imagine, that comes from the basic relationship, because if V is the transverse displacement, then curvature is defined as d2V by dx square. So obviously the relationship, if I invert this relationship, then V is proportional to integral of phi dx. double integral, I would say. Right. So uh, not double integral, it's a double ratio. So second derivative, uh, it multiplies with two length units, and that gives you the displacements. So that's the inverse operation of this curvature definition. So in order to find this displacement, we need to find out what is the if even with inelastic deformation, so that these simple kinematic relations hold. So this plastic hinge concept is defined, so that we can consider this entire plastic curvature to be lumped at one single point, and still work out with basic kinematic relations to find out what is the rigid body rotation and the displacement arising because of that, and add to that what is the elastic deformation, and we can compute what is the maximum tip displacement, maximum and the yield tip displacement. Whereas the region of plastic deformation is the actual inelastic deformation. So when I am talking about earlier in the course, we discussed about spatial confinement steel. To be provided in plastic hinge region. So when I say that spatial confinement steel to be provided in plastic hinge region, it is meant to be provided over the entire length of inelastic deformation, not just this plastic hinge length of the plastic hinge. So this is a very, very important distinction that you should realize, you should appreciate. This plastic hinge length is only a simplifying assumption, simplifying construct to allow us to use the kinematic relationships to calculate the displacements from this curvature. Right? It has really no relation with the requirement of the confinement steel or actual extent of the plastic deformation in the beam. Right? So the entire wherever the special confinement steel is required, that is essentially required whenever you rely on the nonlinear deformation plastic rotations, because steel will not be able to yield properly unless there is enough strain capacity available in the compression zone of the concrete. Unless the concrete is able to take up a higher level of strain, there is no way steel in the tension zone can elongate. So ductility is not possible without confining the concrete. The confinement of the concrete provides you the extends the concrete strain, and the extent is of the order of about 4 to 12 times. Right? So the ultimate strain in compression of concrete under confinement, if it is properly confined, and when it is not properly confined, the ratio can vary from 4 to 12 approximately. So it's a very, very large strain range that you can get by even in concrete compression, that by this confinement steel, and it is that strain range that you will get. Let me just draw the qualitatively the two. So this is confined concrete, Cc is confined concrete, and this is epsilon c is unconfined concrete, and this is of course let's say compression So while confined concrete you may achieve somewhere around 0.0035, and this is the maximum stress. For confined concrete you can actually go up to 'right. So this is what you have. So it can be of the order of even 0.015. So this is for confined concrete, and this is for unconfined concrete. So it is this extended behavior that you get from the confinement of the concrete zone concrete core, that allows you to develop additional yield in the tension reinforcement, yielding to take place in tension reinforcement, because there is enough strain capacity available in the concrete zone of the concrete in the confined zone of the concrete core. So, but when we do this, we also need to take care of the fact that we need to ignore the strain, the concrete which is in the outside the confined core. So that is the cover of the cover region of the concrete. So while your section might look like, whether it is beam or column, your section might look like this. Right? So this shaded portion unconfined concrete area should be ignored if we are relying on the confined concrete strength, because there is no way this block of this area of the concrete can take this amount of this kind of strain. I mean, it will be completely crushed concrete. It is concrete will spall, and all the cover will be coming off if we actually get into this range of strain in the concrete, and which will happen if steel begins to yield, tension steel begins to yield. So when tension steel begins to yield, the strain in the concrete compression zone of the concrete will be in this range, and when it approaches this end, then obviously the unconfined portion of the concrete cannot withstand this amount of strain, and it will crack, and it has to be technically practically useless as far as the resistance is concerned. And therefore you will find that in all design codes, although it is easier to calculate member section properties in terms of gross area, gross section, only a fraction of it is used. So for example, I can use the moment of inertia based on the gross section, but I will use while computing, while using it in my analysis, I will use only 70% of that. So I'll weighting coefficient is about 0.7. So I'll multiply the gross section properties with by 0.7 and use that in analysis, because in case of that is what will be effectively participating in the structural action when this situation arises. The yielding will happen and unconfined concrete will be rendered useless, and it will be spalling off as soon as the concrete is strained beyond this ultimate strain, unconfined strain limit. So you have this recommendation in the design codes, the clause that actually comes from this reason that this cover will be spalling in case of inelastic deformation, and it is only the concrete core within this lateral ties within the confined zone that will be effective. And if I use total cross section area, then I am unnecessarily enhancing the stiffness of the system. I mean, it's more inertia, more moment of inertia, higher moment of inertia, so that will lead to higher stiffness properties, and that will lead to shorter period estimation, and that may happen, that may be creating problem if I happen to fall. If you look at the design spectrum, so if the natural period is somewhere here, and if I estimate the using the gross section properties my natural period to be somewhere here, then I am unnecessary. This leads to so let's say this is T1 and this I say is because of Tg. So T1 is the fundamental period, using cracked section. Tg fundamental period using gross section, isn't it? Because if I use the gross section, the moment of inertia is going to be much higher, and if I use the only the confined core, the moment of inertia is going to be considerably smaller than the gross section properties, and therefore the natural period is also going to be larger. The stiffness is going to be smaller, and that will have effect of having larger natural period. So if I have this cracked section natural period somewhere here, and using the gross section it shortens the period, then I run the risk of underestimating the seismic forces on the structure, and this is entirely because of the modeling assumption. The actual behavior obviously is going to, because mechanics does not actual mechanics does not depend on the assumptions we make. Actual mechanics follows its own whatever the rules of the fundamental rules are there, the natural laws, and if the concrete is not capable of taking this extra strain, it will fail. So irrespective of whether you have assumed this area to be effective or not, it will be ineffective. So your assumptions do not make any difference to the behavior. Behavior is entirely independent of the assumption. It's the other way around. Your assumptions have to be consistent with the expected behavior of the system during the critical conditions that will be at play. So when you look at that, so at that position, when this maximum strain is building up, then this unconfined concrete core is not going to be effective, and your fundamental period is actually going to be somewhat larger than what the fundamental period you assumed using the cross section properties. And therefore, in order to safeguard against this phenomena, against this possibility, the IS code talks about flattening this curve all to the origin, up to origin. That is to safeguard against this possibility of underestimating forces. So if the fundamental period of the cracked section or whatever the fundamental period estimated using the cross section properties happens to be in this ascending branch of the design spectrum, then we just use the forces at the constant amplified level for calculating the seismic forces. So that in a way protects the designer from underestimating the forces and thereby incurring much larger forces and much heavier damage than anticipated or provided for in the design calculations otherwise. So that's the basic idea of the confinement and the ductility provisions. And of course the ductility is confinement or special confinement steel is one way to increase the ductility. The other way is of course by increasing the grade of concrete itself. If you use higher grade of concrete, it has more it tends to increase the curvature ductility in the section, and counter effect is provided by the axial compression. If there is axial compression in the section, then the ductility, curvature ductility is adversely affected. So the columns in general are less ductile. Ductility in the curvature ductility in the columns is in general much smaller than what you will find in case of beams. So but eventually everything boils down to the displacement. I mean, curvature is still a member level deformation characteristic, although it is in a way what we can relate to the material testing, uniaxial material testing, because this curvature is essentially, if you look at it, M by I, F by Y is equal to E by R. So this curvature is essentially equal to the refers to the axial strain in the members. It is proportional, right? So curvature is equal to sigma by YE. So that's epsilon by Y. So this is the axial strain in the deformation in the section, and so it is no surprise that when I said curvature ductility is about 15, that is what you will find of the same order when you look at the material testing ductility of a section, right? And but this ductility is not translated uniformly at a global level when we talk of the deformation of the structure as a whole. So when we talk of displacement ductility, obviously the moment curvature, the curvature ductility is proportional to displacement ductility. So is actually proportional to curvature ductility, but usually very small. And it is also important, mere displacement ductility is not enough. It is also important to know how that ductility, displacement ductility is distributed over the height of the structure. For example, we had discussed this case earlier, probably. So we can have plastic hinges at the beam, and at the base of the column. So in response to the effective lateral forces, there will be some kind of deformation here. So this is the displacement profile. On the other hand, there can be another structure where hinges are formed only at the column. So the deformation is going to be like this. So while the total deformation here delta is same, but it is the relative deformation, how this deformation is spread across the height, that is important. So both the structures, both the frames, they deform by the same amount. If I consider the roof displacement is identical, but this is of course has developed into a mechanism, and this is a incapable of taking any extra load, whereas this is still stable and it can still support the load. So this is a that's why it is important criteria that it's not just the total displacement, or if I just compute what is the roof displacement, it is not just the roof displacement which is important. What is more important is how that roof displacement has come out to be with contribution as an accumulation of inter-story drifts. So roof displacement as an cumulative effect of inter-story drift is what is more important. That is a better characterization of the structural behavior rather than just a gross value of roof displacement. And therefore you will find another uh, criteria for the earthquake resistance is that is the limit on the interstory drift. Total interstory drift should be limited to a certain portion of the height of the story, and that is to prevent this kind of soft story mechanism where the most of the deformations happen in one floor, and rest of the floors actually do not deform, they just move as a rigid body, right? So tomorrow we will start our discussions on the principles of member design. How do we consider the design of the sections and take up from there. I mean, different members, ductile, how the members are dealt with, design of sections dealt with in case of ductile frames, uh, beams, columns, beam column joints, and then we will follow it up with the walls.
Sir,
So, yeah, yes,
sir, the unconfined grade or
नहीं इको आ रहा है, योर वॉइस इज नॉट क्लियर. Hardik, I couldn't hear you. There was an echo.
okay, 10.005. There.
Yes, please repeat. You were not audible for most part.
The strain which we are taking in unconfined concrete, that is 0.035, we are taking it at topmost compression fiber.
Yes.
So in confined concrete, that is 0.015, so where that strain is?
It is at the
topmost fiber.
yes. It is at the topmost.
Fiber of
The strain distribution remains the same. It's only the magnitude or the numbers that change. It is going to be triangular distribution again.
Confined concrete, we are not considering.
Yes, when we say confined concrete, then it is the top fiber of the within the confinement. We don't consider it at the unconfined zone. That's what I told you. That unconfined zone that we had, this portion, that shaded portion, this has to be ignored. So then it is the top fiber of this at this level. Right? So when in case of confined concrete, it is the top fiber of the confined core. Yes, Mohan?
Sir, when we are calculating this yield curvature in terms of this compressive strain, it's concrete strain, epsilon E. So is this epsilon C is the strain at which steel start yield?
Epsilon C is the I mean, when we evaluate this yield curvature based on the concrete compression, that is only when section is over reinforced and steel is not yielding, right? So, but your concrete will start crushing in that case. So it will go beyond the peak stress and then it will come on the drooping curve. For example, in this case, so this strain, this level is approximately of the order of 0.002 strain level, right? So slightly less than is what we call as the at that level 0.0015. After that it begins to droop, right? So cracking has already started here. While the steel, because it is heavily reinforced, so steel is still not yielding. but the concrete has begun to crack, right? So that's why it is called the yield level, because then the moment curvature is going to start drooping again. It cannot take up keep on accumulating curvature.
Okay, sir.
Yeah.
And sir, one statement requesting, in plastic hinge region, we can use the kinematic relationship, like
No, kinematic relations are used for estimating the displacements based on the curvatures, plastic curvatures, and that is, in order to use those kinematic relations, we define this construct of equivalent plastic hinge length, right? So that plastic hinge length is used, is necessary, so that we can model this plastic hinge. Although physically plastic hinge is an extended zone, it is a finite length over which the entire section will undergo extensive cracking and yielding and so on. But for the calculation, when I say hinge is at one point. So I will, in order to facilitate that rotation mechanism, I mean rigid body rotation, when you have hinge, you have rigid body rotation, and that will have implication on what is the displacement at a given length at lever arm. So in order to calculate, that's a kinematic relation. In order to be able to use that kinematic analogy of hinge, I need to define the geometric property which will be consistent with that assumption and the experiment and the actual behavior. What it will be, actual behavior is of course non-linear and very complex, and not really worthwhile the effort when we can get a reasonably good result using these simplified kinematic relations, and the results numbers that we compute in this way are more or less in the ballpark.
and sir, this last one, in which we have shown this soft story, no sir?
Yes, yes.
So when we say this is a mechanism,
It is a mechanism.
sir, but in general we study the mechanism when continuous three hinges were present, then it is a mechanism.
It is a mechanism. It cannot sustain any lateral load.
Okay, sir. Yes.
है ना, पोर्टल मैकेनिज्म तो बन गया वहाँ पर. तो ऊपर की फ्लोर भले ही, I mean the upper floors may not be sustaining any damage, but the ground floor has been converted into a mechanism. It cannot support any more lateral load. Right? Okay, any more questions? Okay, fine. We'll continue tomorrow.